This is the final part of the autoencoder series. In this video, we will implement a variational autoencoder. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last video, we looked at the architecture of a variational autoencoder and created a loss function. In this video, we will implement a variational autoencoder model and generate MNIST images. In the last video, we looked at this variational autoencoder model and derived the loss function as follows. However, there is one thing to consider when actually implementing this model. The standard deviation used to compute z must be positive. To make the output of this layer positive, you can use an activation function such as RealU or sigmoid. For RealU, the gradient is not well defined around 0. For sigmoid, vanishing gradient problem may occur. Both are possible, but can make the training unstable. For more stable learning, this structure can be changed as follows. Let's define this layer to output log variances. Let the log variances be V1 and V2. This formula used in the left model can be written as follows. Then the formula to calculate z can be written as follows. That is, z is expressed in terms of mu and v. This part is the standard deviation. If we set the activation function of this layer to linear, the range of V1 and V2 will be from -infinity to +infinity. And the standard deviation is always positive. This is the same model as the left one, but it is more stable because it does not place any constraints on the output of this layer. The loss function changes as follows. Sigma squared can be written as exponential v, and log sigma squared can be written as v. We will use this model to implement a variational autoencoder. Now let's implement this model in code. Much of this code comes from this site. First, let's write a class that computes z using this formula. The class name is sampling. The inputs to this function are mu and v. Mu's are the means, the output from this layer, and v's are the log variances, the output from this layer. Use this formula to compute z and return the results. Next, we build an encoder model. Set the latent space to have 8 dimensions. Create an input layer of the encoder. The shape of the input data is 28 by 28 by 1, which are the dimensions of MNIST images. Add 2 2D convolutional layers. Then we add a dense layer that outputs the mean and a dense layer that outputs the log variance. Since the latent space is 8-dimensional, each of these layers outputs 8 means and 8 log variances. Next, we add a sampling layer that samples epsilon from the standard normal distribution and computes z using this formula. Create an encoder model. The input of this model is E input, and the outputs are z mean, z log var, and zz. Next, we build a decoder model. Create an input layer of the decoder. The input data is a set of latent vectors of size 8. Then we add a dense layer and 3 2D transpose convolutional layers. Since each pixel value of the MNIST images we use is normalized to a value between 0 and 1, we use the sigmoid activation function in the last layer. Create the decoder model The dimensions of the decoder output are 28 by 28 by 1. Next, we write a class that creates a variational autoencoder model. This class takes an encoder and a decoder as input. The variational autoencoder model includes an encoder and a decoder model. This is a custom model created by subclassing Keris's model. When we need to write our own training loop from scratch, we use a custom model. This allows us to take advantage of the convenient features provided by the fit function of the Keris model. We define a list of our metric objects, which are the binary cross-entropy loss, KL divergence, and total loss. And we define the train step method. When you need to customize what fit function does, you should override the training step function of the model class. In the body of the train step method, we implement a regular training update. Update network parameters using TensorFlow's gradient tape. We feed batch data into the encoder model and obtain the mean, log variance, and latent vector z. Then we feed the latent vector z into the decoder model and get the output of the network. The output of the network is a reconstruction of the input data. Next, we compute the average of binary cross-entropy using the input data and the reconstructed data. The first term of the loss function is the average of binary cross-entropy. Next, we compute the average of the KL divergence using the mean and log variance, which are the outputs of the encoder. The second term of the loss function is the average of KL divergence. Here, D is the dimension of the input data, and K is the dimension of the latent space. Finally, we compute the total loss by summing the binary cross-entropy and the KL divergence. Next, we calculate the gradients of the total loss with respect to the parameters. And then we use this gradients to update the parameters. We update and return the metrics to later see how each loss changes during training. Now, let's train a VAE model and use the train decoder to generate MNIST images. Load the MNIST dataset and split it into training and test datasets. Create and compile the VAE model. And fit this model to the training data. Visually check the metrics measured during training. Finally, generate multiple images similar to a test image. Select one of the digit 5 images from the test dataset. Visually see this image. The result is like this. Now let's generate multiple images similar to this. We feed this image into the trained encoder model and get its mean and log variance in the latent space. We sample a latent vector z from this distribution. We feed the latent vector z to the trained decoder to generate a reconstructed image. Visualize the reconstructed image. Repeat this multiple times to generate multiple images. The results are as follows. Images similar to the digit 5 are generated. Most of them are similar to the original digit 5 image. Some are similar to digit 6 images. This is because the distributions of the digit 5 and the digit 6 overlap in the latent space. The results of generating images similar to the digit 4 are as follows. Most of them are similar to the digit 4 image. Some are similar to digit 9 images. The losses measured during training are as follows. The reconstruction error loss is decreasing, while the KL divergence loss is increasing. The KL divergence is a regularization term in the total loss formula. This may decrease or increase. Here it is increasing like this. This appears to be because regularization is applied more and more as learning progresses to prevent overfitting. Let's run this code. We got the following results. Let's set the latent space to have 2 dimensions and see how the latent vectors are distributed in that space. Here we set the size of the latent vector to 2. The rest of the code is identical to the previous code. Load the MNIST dataset and fit the model to the training data. And let's check the distribution of latent vectors in the 2-dimensional latent space. I will skip the explanation of this code. The results are as follows. The latent vectors of the test data are distributed in this space as follows. The digit 9 images are distributed here, and the digit 7 images are distributed here. Similar images are overlapping each other. Let's run this code. We got the following results. So far, we have looked at autoencoders through a total of 6 videos.